Hello everyone, welcome to the electronic devices course. We are talking about chapter number 2, operational amplifiers, and our today lecture is the lecture number 2 in the series. In the last lecture, we talked about that we ended up finding the ideal terminal characteristics of an op-amp. We also talked about that we never use op-amps in almost all the applications. We never use it in the open loop configuration. We always have the op-amp terminals connected to some passive elements like resistors, and we use that in different configurations. We introduce the terms inverting and non-inverting configurations. And today we are going to discuss one of those inverting configurations today. In the last lecture, we also talked about a differential and a common mode gains. We talked about the common mode gain is 0 since it is taking a difference of the two signals. So the common mode gain is 0 and the differential gain is A, which is we kind of labeled it as A, which ideally is infinite. Today we will start this lecture by defining these common mode and the differential signals and their representation in terms of the input signals V1 and V2, and then we will start building our different configurations of these amplifiers. Again, we're going to start with inverting and then we will move to a non-inverting configurations. Okay, so let's start our today's lecture. We're going to start with differential and common mode signals. Okay, so let's define the differential signal first. Differential, sorry about the spellings, differential input signal, let's call it as a VID, is the difference between two input signals at op-amp. Alright, right, so we are defining a differential input signal as the difference of the two input signals, right? So our VID will be equals to V2 minus V1. Let's call it as an equation number 1. Now let's define the common mode signal. Common mode signal, which is the common components that are present in between both the signals, is the average of the two signals. Is the average of the two signals, right? So let's define VCM, this common mode signal, as VCM, CM common mode. So the common mode voltage over here will be V1 plus V2 over 2. Excuse me. Okay. So we have two equations. So let's solve these equations for V1 and V2. So if we solve this for V1 and V2, from equation number 1, we can find out the value of V1. V1 equals V2 minus VID. And from equation from 2, we can find out the value of V2. So it will be, this will go over here, 2 VCM minus V1 equals V2. So I am going to put this V2, so put V2 in equation 3 and let's label it as 3. So it will be V1 sorry, equals 2 VCM minus V1 minus VID. So this will be equals to 2V1 equals 2 VCM minus VID. V1 equals VCM minus VID over 2. So this is how I can express my input voltage 1 as the combination of a common mode signal and the differential signal. All right, so similarly, if I will put down this equation now, my V2 will become equals to 2 VCM minus, right? So if I will put this V1 now, if I have to find V2, so let's put this V1 back over here to calculate V2. So V2 equals 2 VCM minus V1. Minus V1 is minus VCM plus VID over 2. So V2 will become VCM plus VID over 2. So this way we ended up expressing both input voltages V1 and input voltage V2 as a combination of a common mode and their differential parts. Now let's see how we can represent in the form of circuits. All right. So let's see. I have this positive. Let's suppose this is my V1 signal, and let's suppose this is grounded, and this is the terminal number 1. And similarly, let us suppose this is my V2, and this is my second terminal. This can be equated to, this should be 3 lines, right? So this can be equated to, and I'm gonna just show you how I did that in a second. 1, 2, VID over 2, VID over 2, and this is VCM. So this is V1 and this is V2. All right, right? So in the last slide, what we found out is our V1 equals here, right? So this is our V1. Our V1 equals VCM minus VID over 2, right? So if I go back here, I can see that my V1 voltage equals VCM and then minus VID over 2, and my V2 voltage equals VCM plus VID over 2. Sorry, right? So VCM plus VID over 2. So this is how I can express both of them in terms of my in terms of the common mode and the differential signal. Let's see if I will put these two signals now. If I will put this combination into the op-amp, right? Negative, positive, V naught. Right? So my V naught is A times V2 minus V1. Right? So let's do V2 minus V1 now. So V2 minus V1 equals, so what is V2 from here? So V2 is VCM minus plus VID over 2 minus V1 is VCM minus VID over 2. So it will be VCM plus VID over 2 minus VCM plus VID over 2. So VCM will be cancelled out and we are going to left with VID over 2. Right, so this shows that we can so this shows that our again operational amplifier is taking a difference of the two while rejecting the common mode signal that is present in between the input terminals. And what we have done is we have expressed V1 and V2 signals in terms of their common mode and differential counterparts, and then we have applied these signals to the operational amplifier and found the output voltage. And our output voltage is a differential voltage, and the common mode signal was rejected. All right, excuse me. All right, so in the second part of the lecture now, I am going to start talking about the configurations that we that we hinted upon in the last lecture, right? So we again said that we have an ideal op-amp, has an infinite gain, infinite bandwidth, infinite input impedance, zero output impedance. But we don't use that in the open loop configuration. So we use that with the passive components like resistors to develop different configurations to be used in different applications. So today we are going to discuss one of those configurations. Our first configurations that we are going to discuss today is the inverting configuration. So let's see what is an inverting configuration. So we have these two inverting and non-inverting inputs. This is our output, right? So I connect this to the input voltage Vi. It is connected to the resistance R1. I connect another resistance in the feedback from output to the input 1, the resistor R2, and then I ground the second input V2, second input terminal. So this is how we can use, and this is our grounded plus minus V naught here. Okay, so this is the configuration in which we can use our operational amplifier in the inverting configuration. And what we are going to do in this lecture is we are going to see its characteristics, and we are going to find out the gain of this amplifier. So some things that we can see, some of the differences that we can see over here is we have this resistor R2. So this resistor R2 is applying negative feedback. We're going to call this resistor R2 to applying a negative feedback because it is taking the output voltage V naught, right? And connecting it to the input terminal 1. So let's suppose that if R2 is connected between V naught and positive terminal, then we will call it positive feedback, right? So we are calling it as a negative feedback because it's a resistor that is connecting the output voltage sorry, output voltage terminal to the inverting terminal. If we would have another resistor in between V naught, right, if we would have a resistor over here, something like that, then this thing would known as a positive feedback. All right. Okay. So for this lecture, we are interested in the inverting configuration or a negative feedback. R2 is also closing the loop. All right. So let's define our gain of this closed loop amplifier. So let's define a closed loop gain. So the gain of this closed loop amplifier is, I'm going to symbolically represent it with a capital G. So it will be V naught, output voltage, to the input voltage, Vi. Okay, now let's draw the equivalent electrical circuits of this amplifier. Okay, so equivalent circuits. All right, so I'm going to draw the equivalent circuit over here just to get more space here. So I have this negative, sorry. Okay. So negative, positive. R1, a resistor, R2. This is terminal number 3, plus minus V naught, and this is terminal number 1 and 2, and we know that this is V2 minus V1, this is VI, and the current that goes over here is II. Let's say the current that goes over here is I2R2. And we have a voltage control voltage source here, plus minus, which is A V2 minus V1. Alright, so this is the very detailed representation of our inverting configuration, where we have a resistance R2 in the feedback loop from the output V0, third terminal, to the first terminal, to the inverting terminal. So if we look closely, we already know some of the characteristics of this amplifier is that no current, so this 0 over here represents that no current will go into the input terminals. Currently I'm assuming the amplifier to be an ideal, our op-amp to be an ideal, then no current will go into the input terminals V1 and V2, 1 and 2 terminals. Plus we know that we have this voltage dependent, voltage controlled voltage source. A is our open loop gain, which is ideally infinite, and it is taking the difference of the V2 minus V1. I over here is the current drawn from the source voltage or the input voltage VI over here, but this current will never go to the terminals because of infinite input impedance. And then we have a current I2 that is flowing through this branch, I2R2. Essentially, since we know that this current is 0, so I already know that my II will be equals to I2. But we are going to come back to this point again. So let me simplify this circuit a little bit more. Okay, so if I have to draw a simple circuit, my simple circuit is going to look like negative, positive, this resistor, V naught, R2, R1, plus minus input voltage VI, and the non-inverting input is grounded. The current drawn over here is II. And now since we know that no current will go over here, right, so our no current will enter over here, so all the current will move over here. So we are going to have a same current that is going to flow through this resistance R2. All right. Now we are going to look into its characteristics into a little bit more detail. All right. So let's assume an ideal op-amp. Right, so since we know that our differential gain A is ideally infinite, right, so our V naught, which is equals to A times V2 minus V1, can be written as V2 minus V1 equals V naught over A. V naught over infinite should be equals to 0. So this means that our V2 should be equals to V1. So V2 equals V1 means that the terminal voltage that is appearing at right, so our V2, we know that it was a non-inverting voltage that is appearing over here, right? this voltage is V positive or V2, right? And the voltage over here is V negative, also V1, V negative. All right, right? So this shows that both of these voltages, terminal voltages, will be the same, right? And this is because of infinite gain, the voltage at both op-amp input terminals will approach to be equal. Right? So this statement, right, since the voltages in between both of these terminals will be the same, we can say that this is a virtual short circuit. This is a virtual short circuit between inputs 1 and 2. All right. Now, if I look over here, right, if we look closely at this terminal is grounded, right? So this means that my V positive, which is equals to V2, is grounded, it is 0 volts. And if this is 0 volts, this means that V1 should also be 0 volts. And if both of them are 0 volts, so this means that there will be a virtual ground that will appear at this terminal as well. And the voltage in between these two terminals will be 0 volts. Right now, so since V2 is 0 volts grounded, this means that V1 is 0 volts as well, or V positive equals V2 equals 0 volts, and V negative equals V1 equals 0 volts. You can express the terminal 1 and 2 either as V1 and V2 or V positive and V negative. Pick one notation. I'm just writing both the notations because sometimes the book alternatively use these two notations, so I thought I can express that. But in later part of the course, or this chapter, I am only going to use one of these notations. Okay, so since now our V2 or non-inverting terminal, positive terminal of the op-amp is grounded, so this means that our inverting terminal is also grounded. This is the important thing to notice. Our terminal 1 is a virtual ground, right? So we are going to call it as a virtual ground, right? So this is not physically grounded, right? It is going to behave as a ground terminal, right? So that is why it is called as a virtual ground. It is not physically connected to the ground terminal. Please make that difference. Note it. All right. All right, so second, let's find out the value of the gain. From here we can see that let's find out. So this current II, that is the current that is drawn from the input and is, sorry, where did it go? Okay, this is drawn from the input II. It is flowing in through the resistor R1, and since our V negative is grounded or V1 is grounded, so the same current II will flow through R2. So I'm going to do it stepwise. So the second point, find current II through R1. All right, so let's find out this current II through the resistor R1. So I can see it from here. This is one of the node and this is the second node, right? So we can easily use Kirchhoff's laws to do it. So our II is going to be the difference of the voltages divided by the resistance. So II will be equals to the VI minus V1 over R1. We know that V1 is 0 volts because it's a virtual ground. So our II will be equals to VI over R1. Right? Then we said that the same current will flow through R2 because of infinite input resistance. Input resistance is infinite and op-amp will draw 0 input current. So this means same current II will flow through R2. So our V naught, so now if we apply a Kirchhoff's law over here, if we are trying to find this II over here, right? So if we apply the Kirchhoff's law at the output voltage V naught, so V naught equals V1, which is this terminal, this node, right? Or a V negative minus IIR2, right? So our V naught will becomes equals to V1 minus II R2. Again, note that V1 equals V negative. I'm alternatively using both of them. So V1 is 0 minus II R2. So this means that V naught equals minus VI over R1 into R2. If you take VI over here, what you will get is V naught over VI equals minus R2 over R1. Alright, so this is the gain that we wanted to find, the closed loop gain. V naught over VI equals minus R2 over R1. This was a closed loop gain of the inverting configurations that we were interested in finding out. Note negative sign over here indicates the output will be 180 degree phase shifted, right? There is a 180 degree phase shift and output. Second, we will have a negative feedback here. Negative feedback. This negative sign also indicates that we have a negative feedback. So that is why it is also known as inverting configuration. Right? And so the final point before I wrap up our lecture over here. So the final point over here is that we have our open loop gain was infinite for an ideal op-amp or an extremely large gain. And what we ended up doing is, rather than using that, we ended up using this inverting configuration and ended up converting that into a much more reliable gain, much more predictable gain that we can design. So we can select these different values of R2 and R1 to design our amplifier circuit to achieve a desired value of the gain that we want. So this is the inverting configuration. In this lecture again, let me give you a couple of minutes recap of the lecture today before wrapping it up. So we started with talking about the differential and the common mode signals. Right, differential signal is the difference of the two signals. Common mode signal sorry, can be represented as an average of the two signals, and we ended up developing its different driving its equations and developing its circuit representation. And we saw that when we apply those circuit equivalents to the op-amps, our op-amp will subtract out or take the difference. When we are going to take the difference of those inputs, it will take out the common mode signals, and the output that we will get will be a differential signal. Then we started with talking about the inverting configuration, that we have a resistor R2 in feedback, creating a negative feedback. And what we wanted over here is to find out the value of the closed loop gain. The important thing over here in this configuration is that the current drawn into the input will be 0, assuming an ideal op-amp, a very high impedance, input impedance. ID is infinite for an ideal op-amp. And then we have the current that will flow through this resistor will again gonna flow through a resistor R2 as well. And using that, we ended up finding out the two equations. Another important thing that we learned over here, if our gain is infinite, then our voltages at both the input terminals, this negative terminal and the positive terminal, will be the same, will approach to be the same. And since our positive terminal is grounded, so this means that our negative terminal, there will be a virtual ground in the negative terminal. It is not physically grounded, but it will appear to be grounded. And in that case, we are going to have a virtual short circuit in between these two terminals. And we simply ended up finding the value of II through resistor R1. And we ended up applying a Kirchhoff's law at the output terminal V0 to find out this closed loop gain, which is minus R2 over R1. And we can select different values of R2 and R1 to design our amplifier and to achieve a desired gain. The negative sign over here again indicates a 180-degree phase shift output. Alright, so this is the basic kind of a derivation of a closed loop gain. In the next lecture now, we are going to very quickly make another quick derivation of what will happen to the value of the closed loop gain if our open loop gain is not infinite, right? So for an ideal amplifier, we said that our value of A is infinite. What will happen if this is not infinite, right? So we will drive another expression for the gain of the inverting configuration when it will not be infinite. So we are going to, and we will also do one more example in the next lecture. All right, so with that, thank you so much. I will talk to you in the next lecture. Bye-bye.